will make 2 hours of substitution, and there won't be any attendance quiz, but we have to proceed as much as possible. So, but anyway, the lectures are being recorded, so for those of you who cannot attend, may just watch them, hopefully. Today we will start an important topic of system analysis and the definition of systems, the properties of systems. But before that, we have forgotten one distinct type of a periodic signal, which is called a complex exponential. The continuous time complex exponential, or the complex exponential in the form of an angle in general, is something that we constantly use, including Fourier transforms and such things. This is a periodic thing, e to the j theta, with respect to the angle theta. And if we are thinking of signals, what you can say is, for example, something like this: e to the j omega t and e to the j omega n. These two are, in many cases, periodic signals. This is certainly a periodic one, but this is, under some circumstances, a periodic thing, depending on the proper definition of a frequency, which corresponds to an integer period. Because we know that for discrete time signals, integer period is necessary. Otherwise, if the period is, for example, 7.2, let's say, then we cannot say so. The period must be an integer, always. If it is 7.2, by the way, it is safe to assume that the period is in fact 72, 10 times of that, where it becomes an integer. E to the j omega t is equal to, from the Euler's theorem, cosine omega t plus j sine omega t. Okay, that's the expansion of a complex exponential. And you have to always remember these things. And conversely, any cosine or a sine can be represented in terms of e to the signals. For example, what's a cosine omega t then? It is, in 1 over 2 parentheses, e to the j omega t plus e to the minus j omega t. So strangely, if you are calling this omega to be the angular frequency for a complex exponential in this form, e to the j omega t, then cosine omega t has technically 2 frequencies. Why? Because one of them is the frequency of e to the j omega t, the other one is the frequency of e to the minus j omega t. What's the frequency, the angular frequency of e to the j omega t? It's omega. What's the angular frequency of e to the minus j omega t? Minus omega, exactly. That is minus omega. But physically, of course, a negative frequency doesn't make sense. Minus omega will correspond to a period of minus capital T, but that's the same distance as capital T. So it corresponds to the same period. So what is this? We will see that this is a technical and mathematical detail, and it will be very beneficial for us in the analysis called the Fourier analysis and the Fourier transform. We will cover the whole lecture starting, like, I don't know, maybe next week or the week after that. We will start with the Fourier transform, and there you will see that we can define negative frequencies, but that's nothing but a definition. It's something not very physical. It's very mathematical. So these are the definitions that you have to keep in mind. And if this is your signal e to the j omega n in this form, then of course the same definition is valid: cosine omega n plus j sine omega n. Let's not forget the definition of a sine, by the way. Sine omega t. Because this is usually more meaningful as compared to the imaginary part, which is sine omega t. That is equal to 1 over 2j, strange, right? E to the j omega t minus e to the minus j omega t. So this will produce more awkward expressions. There is a 1 over 2j, for example, instead of a 1 over 2. And there's a minus sign as opposed to this plus sign. But apart from that, it also has two components of frequency. One of them is omega, the other one is again minus omega. So a sine and a cosine will have the same frequency content. They don't have the same frequency content, but they appear at the same frequencies. Because, well, obviously, they have the same frequency. There's just a phase difference between them. Now, if you think of a j omega n, this omega must be in this form to make it properly periodic. And this must be the frequency, the angular frequency. So any angular frequency should be expressed in this form. And this capital N is the period then. This is also valid, or instead of this you can also have this kind of a form, k times 2 pi over capital N. This is also a valid discrete time periodic sequence, but the period will then be not capital N but k times capital N. But they are just convertible to periodic sequences. So a discrete time complex exponential or a sinusoid is periodic if the period, if the frequency component is a rational multiple of 2 pi. There must be a 2 pi in it. If there is no 2 pi, then you can never come up with a periodic sequence. For example, so this is okay, but let's write this time as a cosine, because cosine can be split into complex exponentials using these formulas over there. For example, let's think of this, cosine n. What's going on over here? Can you find an integer, capital N? Is it ever possible that this may become cosine n plus capital N? And what is this capital N, provided that it's an integer? We know that this capital N should be 2 pi. Normally, in terms of angles, if you consider this inside term to be an angle. So this capital N must be 2 pi. But it must be integer, so let's multiply it with larger numbers, larger integers to make it an integer. For example, as I say, if the period is 7.2, it can't be 7.2, but we can always multiply it with any integer like this to make it 72, and that's fine. Now, is it possible for pi, so that when it gets multiplied with an integer k, is it possible? That's not possible, right? Because that's an irrational number. Only rational numbers can become integers by multiplying with the denominator, rational number. This is an irrational number, and you can never get an integer out of it. So the conclusion is, therefore, it's never like this for any integer n. So this is aperiodic. All right. So be careful about the periodicity definitions of discrete time sinusoids or discrete time periodic signals, so-called. Without being periodic, you shouldn't start the analysis with that assumption. So first you must check whether it's periodic or not. Periodic signals will have their own characteristics and analysis methods, tools. The others, non-periodic ones, will have different tools. Okay, so let's not forget about that. Now we can start with systems. I have some shapes over here. For the descriptions of systems. Now, a system acts upon functions or signals in this case, and they have some properties, and they must be analyzed simultaneously with signals. Whenever I say systems and they act upon signals and things like that, we must find a way to formulate a system. So the main question is, how can we formulate a system? I want you to write down a system. How can you do that? You are engineers, you're supposed to design systems. Suppose you designed a system and you solved the problem, an engineering problem of your boss. And then your boss asks you, okay, show me the system, or explain. How do you explain? How do you describe a system? What are the description methods that you know for systems? Mathematical modeling. What do you mean with that? How do you model a system then?
Sistemdeki bazı şeyleri matematiksel olarak ifade etmeye çalışıyor.
Okay, you try to represent some issues of the system mathematically. What are those issues? That's the question.
Örneğin hız. Yani sistemin hızı, yani hızlı bir şey var ya da kütle.
Okay, so the speed, the mass, all right. Those things are parameters of your observations. So your observations are usually signals. So you are saying that you could measure the signal out of it. It produces a signal, and the signal has some properties, like the speed of it or the mass of it, for mechanical systems, for instance. But that's the output. So what I would expect from this answer is something like this. Let's measure the output of it. Let's plot it. Let's give the value or the magnitude of the output. That is something like that. A system can be formulated, therefore, with respect to its output. Let's not forget the input as well. So the first methodology could be the input-output behavior, let's say. According to this input, the system will produce this output. For example, if I give you 220 volts to this machinery, it rotates at a speed of this. The input is 220 volts of line voltage, a sinusoid, and the output is a rotating machinery rotating at some certain speed. That's the output. So the input-output relation. The input-output relation will have its problems for the representation or the formulation of the system because let's start with discrete time. This is your system. This is your output. You usually give a particular example input. You may think that, for example, for a machinery that's working by itself, we don't have any input, but you usually have it. I mean, if the system is working by itself, it should need some electricity at least, or something that initiates or starts. So that's an input, and you observe the output. In many engineering problems, this input is constant, like 220 volts. So you take a look at the output. If it fits you, you have designed your system. It works. Because the input is always the same. But mathematically, if you want to describe a system, you should also give us the information that what if this input changes? What happens to the output? So the input-output behavior must be provided independent from the input. For any input, the output is like this. That may be a definition for the representation. For example, you can say, that may be an example, y of n is equal to the square of its input, for instance, minus 2. Okay, that's an input-output relation. Or y of n is equal to 2 times x of n minus x of n minus 1. Now what's that? What is x of n minus 1? It's the previous sample. So the input is constantly coming. It's continuously coming for different n's. And the output is always produced as twice of the current input minus the past input. Let's give an example of a system like this. Y of n is equal to x of n minus x of n minus 1. So there's no 2 sign here, but just one simple x of n minus 1, which was one of your quiz questions, as a matter of fact. I was asking you about the similarity of this thing to a derivative. Now, does it really work as a derivative? And what are the practical uses of such formulation? This has a specific name, by the way. This is the first difference. Instead of the first derivative, which is d by dt of x of t, this is the first derivative. But they have some similarities. For example, if your signal is constant, if it doesn't change, we know that the derivative is 0, right? For a flat function. Because the derivative will give you the slope. Now let's assume that your signal is also constant. For this particular position of n, x of n is this, x of n minus 1 is here, so this is n minus 1. So x of n minus 1 is here, so x of n minus x of n minus 1 is 0, because they are the same things. You subtract 1 by 1, and you always get a 0. Now this thing, the first difference is, for example, very practically used in so-called image processing, which is a two-dimensional concept. But in image processing, you can literally use this thing to detect abrupt changes. Let's focus to the same example, and let's extend it to the left like this. Now, you can assume that, well, of course it is one-dimensional, but let's assume that it's a row of an image. So you slice an image, so along any row you have some profile. You cut the image, and this is the profile that you get. These zeros indicate a black, and these non-zeros will indicate a brighter portion of the image. So the transition from the black to, let's say, white, here you have a transition, and that is the edge of a shape, probably, inside the two-dimensional image. When you cut, these are black portions and these are the white portions. Now, can we just locate this position where the transition occurs? Let's apply this. xn minus xn minus 1 is 0 at the output. xn minus xn minus 1 is 0 at the output. xn minus xn minus 1 is 0, xn minus xn minus 1 is 0 for all these n positions, which we slide, of course. And suddenly here, at this point, xn minus xn minus 1 is, I don't know, some number, let's say 1. And then xn minus xn minus 1 is again 0, xn minus xn minus 1 is again 0, 0, 0, 0. It goes on like this. So this is the sequence that you generate as the first difference system that you have. And this system indicates something like this. You can make a thresholding then. If it is below some value, there may be some fluctuations because usually the real life captured images are not perfectly white or perfectly black. They may have some fluctuations, but these will provide lower magnitude numbers. The differences will be small, and suddenly the difference will be large. So you apply a threshold. If this transition is above some threshold, you locate that pixel coordinate to be an edge position, and you detect an edge over there. That's exactly how edge detection works in image processing. For every row, let's assume, okay? Something like that. So, let's come back. We can formulate a system using input-output relations. But for that, it must be in the form of representing the output as a function of the input always, so that for every input we can determine the output. It's not for a single output, for a single input, a single output. Usually systems are not expressed like that mathematically. We have a nice input-output representation formulation in continuous time as well. In discrete time, I gave you this example, 2xn minus xn minus 1, or xn minus xn minus 1. And I said that it's the first difference. We can extend the examples in discrete time like this. Yn could also be 1.5 xn minus 0.5 xn minus 1 plus xn minus 2. This is also possible. Just another example. This is a second order difference equation it becomes. Because the first difference is here, or the first passed sample is here. The second passed sample also appears, so it makes the whole expression to be a second difference equation. This is something that you may be unfamiliar with because you don't know difference equations, but I'm sure you all know differential equations. And differential equations are also input-output relations, I/O relations. As a matter of fact, for continuous time systems, that's what we are usually looking for. We look for a differential equation to formulate the system. Let's give an example of a physical differential equation system, which is a circuit again. In our previous example of a circuit, I gave the output with respect to one single input, which was a rectangular box input, and the output was like this, with a capacitor and things like that. But I want to have a higher order differential equation, so it won't be an RC circuit, but it will be an RLC circuit now. This is the resistor, we have an inductor, and we have a capacitor. The input is x of t, this is the resistance, this is the inductance, this is the capacitance. The output we measure as the voltage across the capacitor, which is y of t. So y of t we want to obtain in terms of x of t. From circuit theory we know the solution to this problem. We know how to solve, we should know how to solve circuits. We write the voltage division equations and the current loop equation. And for example, using this current to be an auxiliary variable of I of t, we have an intermediate output then. The intermediate output is I of t. R times I of t. Notice that it's time varying, it's changing in time. Probably you know how to solve circuits using this current as I only, not changing in time. You just say it's I, it's the current. but it's a function of time because the input voltage is changing in time, so the current is also changing. So it is R times I of t plus L times the derivative of the current, the change in current. Plus the voltage across the capacitor, which we already defined to be the output y of t, is equal to the input. So this is the voltage across the resistor, this is the voltage across the inductor, and this is the voltage across the capacitor, which is already y of t. But I of t is related with the voltage across the capacitor already using this formulation, y of t. The derivative of the voltage across the capacitor times C is equal to the current. That's the behavior of our famous capacitor. So let's substitute, instead of I of t here and here, let's substitute this one so that the whole equation will be in terms of y of t, and I of t will be eliminated from the equation. So this will become L times, I will first indicate this portion because there is already a derivative of I of t, and I of t is already a derivative of y of t. So the second derivative will come. There is an L here, there is an extra C here. LC, the second derivative of y of t. Then let's take this one, R times, there is a C coming from the second equation, d by dt y of t, and then y of t itself is equal to x of t. This is the eventual equation I'm looking for. It is an input-output relation, but it is a little bit different from this one because the differentiation or derivatives are on y. It's not like y is equal to derivatives and scaled versions of the input, but the output is differentiated, and that's equal to x of t. But that's a differential equation form that we are very comfortable with. We should be very comfortable with. So this is an input-output relation that we already know. Now, strangely, such second-order differential equations exist in various other concepts, not necessarily in electrical engineering. And the example that I will show you is a reason why signals and systems is also being taught in, let's say, mechanical engineering departments. Mechanical engineers are also very keen on signals and systems. And the example is here. You have a wall here, and to the wall you have a spring and a damper attached to a mass with mass m, and the spring constant is k and the damper constant is d. This is then a mechanical system, and we are applying a force of x of t, which is the input. We are pulling this mass on a frictionless surface, let's say. Or the friction could also be incorporated, if you wish, into the equations. But let's not do that for the time being. And the position of the mass, initial position, is assumed to be 0, and the output is measured as the position of this mass. How does it move according to the force that we apply? Pulling or maybe pushing as well. It doesn't really change anything, as long as the damping and the spring constants will behave similarly for pushing and pulling. Now there is an acceleration. There is a net acceleration to the system, and that acceleration produces a net force. That net force is nothing but m times a. Okay, that's the force, m times a. A is acceleration, and acceleration is by definition the second derivative of the position. The first derivative of the position is velocity, the second is acceleration. And that is the net force, is equal to rightwards, let's say positive, is the applied rightward force. The other forces are in the other directions, and they behave like this. This spring constant is inversely proportional to proportional to the amount of displacement. The force that this applies leftwards is k times the displacement. The more displacement, the more it pushes back or pulls back towards the wall. And minus, there is a damping as well. That damping is by definition working by the velocity of the overall mass. So that's interestingly the case that if you are pulling slowly, then this damper doesn't react. But if you pull abruptly, then the damper will show more resistance. That's how a damper works. So this is the equation. And from this equation, in fact, the whole equation is already here because there is no auxiliary variable like the current over there. This time, everything is in terms of x and y's, but to make it more handsome, let's collect all the y terms at the left-hand side. And plus k times y of t. And let's isolate x of t at the right-hand side. It's equal to x of t. And this is the differential equation that formulates this mechanical system. And strangely, it's exactly in the same form as this circuit over there. Only the parameterization is different. But with proper values of m, d, and k, these two are the same equations that we have. So that's why mechanical engineers are also working on systems, and electrical engineers are also working on systems. But we interpret or we design our systems using different tools. Mechanical engineers probably use their tools, whereas electrical engineers use their tools of resistors, inductors, etc. Tomorrow there may be other components that may be necessary for an engineer. Okay. Now, how do we solve these differential equations is something. And we know that in solving differential equations, in the case of second order and first order differential equations, we come up with exponential terms usually. And there are two solutions. One of them is the particular solution. And that one depends on initial conditions normally. Right? So we must assign some initial conditions. Initially, was this moving already, for example? Or initially, was there some voltage across the capacitor C? That is necessary. That particular solution will not be interpreted too much in detail in this course. We're not interested in that. The general part, the part which is independent from the initial condition, will be the description of the system for us. Because the description is for the whole system. It shouldn't depend on the initial conditions or anything. Of course, your solution will depend on initial conditions, but we don't care about that. And we won't solve that particular part using our new techniques that we will learn. All right. We have seen these examples already. So these are some examples of input-output relations, but we will have some other representation styles as well. The other representation thing is possible, let's say of course, but it depends on whether the system satisfies some certain properties or not. Otherwise you need to have input-output relations, and not every input-output relation is as simple as a differential or a difference equation. This of course under certain property assumptions must be elaborated, and for that we must list the properties that we can measure for systems. What are the properties that we may think of for systems? For signals, we said the properties are like discrete time and continuous time, periodic and non-periodic, random, power signals, energy signals, and finite support signals, etc. All of them are properties of signals that we may think of. For the systems, the properties are a little bit different. Let's start with the first property that we may think of, and let's start by memory. What do we mean by memory? Do you remember the example that I have erased right now? Y of n is equal to x of n minus x of n minus 1, for instance. This input-output relation indicates that in order to evaluate the output, you must remember one past input, x of n minus 1. One input at the yesterday's input, or 1 hour or 1 millisecond before's input. In that case, you say that the system is with memory. But, for example, if y of n is equal to x of n's square minus 2, if this is your example, then there is no memory needed. We don't need to remember the past inputs anymore in the input-output relation. And such systems are called memoryless. They don't have a memory. I guess you should be able to define whether a system is with memory or memoryless by just inspecting the input-output relations. Okay? That wouldn't be very difficult. If it requires past inputs, then it is with memory. If it doesn't require past inputs, then it is memoryless. Let me give you a very small example here. Is this memoryless or with memory? Y of n is equal to summation k from minus infinity to n x of n. What can you say about this? It is? It is not memoryless. It is with memory, because this n is the current time, and as you see, from minus infinity up to that time, it requires the values of the input. It is extremely with memory. It needs infinite memory, as a matter of fact, far from being memoryless. Right? You have to be careful about this. By the way, such a system is an accumulator. And accumulators are something of particular importance. In continuous time, for example, we do have one accumulatorly behaving component, circuit component, or electronics component. What is that? This, oh, sorry. Maybe that's why you're misled. Yeah, okay, maybe that's why you're misled. Sorry about that. Of course, it's x of k, otherwise k from minus infinity to n. N is here and n is here, it doesn't make sense, right? Sorry about that. Of course, now, this must be x of k, of course. We are accumulating all the past samples and the parameter running index is k. Okay? I hope this is clearer now. Now the continuous time a counterpart of the accumulator that we know of is this, the capacitor. A capacitor is an accumulator because it provides a voltage to be equal to a coefficient, which is the capacitance, by the way, times from minus infinity to t all the currents. Now let's not fall into the same trap over there. That shouldn't be x of n. Here it shouldn't be I of t. Let's use something else. Now I want to use tau here because you should become familiar with this tau Greek letter. I usually replace or substitute t with tau as an auxiliary variable, not lambda. Okay. Lambda is also possible, but this is more classical, and in the book you will mostly encounter tau. So from minus infinity to t, all the currents must be accumulated to find the voltage. Of course, you usually don't know from minus infinity. I mean, who would know what happened in the beginning of the capacitor? So instead of that, you may say that it is from some time, some starting time, let's say 0 to t I of tau dot d tau, plus the initial voltage across the capacitor, the starting point. That's also possible. But nevertheless, it doesn't change the idea. This is an accumulator, and it is a system example with memory. Now let's continue with other properties. A technically important property is invertibility. Is it invertible or not? Is the system invertible? What do we mean by that? An invertible system should let us have such a situation. If this is the system which is invertible, then you should always find an inverse system to get back to x of t at the output, and in the middle you get a y of t. So the input-output relation of S is x of t is producing y of x of t is producing y of t, and the inverse system must make y of t to produce x of t again back. This is we don't have the necessary tools to analyze this in more mathematical detail as we did in memory. For some systems, we know that its inverse doesn't exist using some of the tools that we will learn, like the Fourier transform or the Fourier responses, spectrum responses, so-called. We don't know them yet, so it's a little bit difficult, but let's have an idea about this invertibility for the time being. And let me point out that you should be responsible from questions like, is this system invertible or not? Question. You should solve it in an ad hoc manner, so that if you can find the inverse, then it is invertible. If you cannot find the inverse of the system, if you cannot think of the inverse of a system, then you say, well, it's probably not invertible. So you will start by the examples, and I promise not to ask very hard questions from this for the first examination if you don't know the tools to detect whether it is invertible or not. But this thing is an amplifier. It multiplies the input by 2, and this dot is the replacement of the input, and the output is y of t is of course invertible because You can multiply in the next time with a half to get back to x of t. That's a trivial example. How about this example then? The system I am expressing as an input-output difference equation the accumulator again. This is an accumulator and it accumulates all the past inputs up to, this is not infinity, okay, it's n, up to the current index of n, and that accumulation number provides us with the output y of n. Is this invertible? You may suspect that since I'm giving you this example, this should be invertible. But the problem is, can you find the inverse? It may be easier to remember the inverse of this, the thing that I have erased. Y of t is equal to, from minus infinity to t, x of tau d tau. That's the integral. That's the integral of x. And the inverse of this is known as the fundamental theorem of calculus. So since you're not first year students, you know calculus, you passed calculus, but then you must know the fundamental theorem of calculus. That's the name. The fundamental theorem of calculus. What is it? The fundamental theorem of calculus says that integral is the inverse of derivative. Okay, so if you take the time derivative of this one and this one, you must get x of t. So the time derivative of this integral is equal to x of t. That is the fundamental theorem of calculus. This is behaving similarly. It's not integrating, but it is accumulating. And what is the discrete time counterpart of derivative then? It was difference. Let's think of this system. Z of n is equal to the output is equal to the input of y of n minus y of n minus 1. The first difference. Is it the inverse system? In other words, is z of n equal to x of n? Shall we try? Can you see that you get back to x of n when you say y of n minus 1? Let me indicate how you should see it, then we give a 15 minutes of break. Here at the top, this one is from minus infinity to n. So what is the summation? Dot 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 plus x of n minus 3 plus x of n minus 2 plus x of n minus 1 plus x of n. This is y of n, isn't it? What is y of n minus 1? That's equal to dot 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 plus x of n minus 3 plus x of n minus 2 plus x of n minus 1. Stop, because it's up to n minus 1. So what's the difference between them? When you subtract, everything will be cancelled and you will be left with one final term of the summation in the original y of n. In this y of n minus 1, you sum up to x of n minus 1. So this is left. Therefore, y of n minus 1 is x of n. So that is the inverse system of this. Here the input was x and the output was y. Using this system, the input was y and the output is back to x, which is this definition of invertibility. So this is an invertible system. Difference and accumulator are inverses of each other. in terms of systems. The opposite is a very nice exercise, by the way. If you think of this one, if you say y of n is equal to x of n minus x of n minus 1, which is the difference, what is the inverse of that system? The inverse of that system is an accumulator. It really generates the same output if you cascade that system, different system, and the accumulator system in this order. The input will be the same as the output at the very end. But that one, I strongly recommend you to work it out. Just see it, just do it. And see that you obtain the original signal at the output. We did it for this order, accumulator first, differentiator next. Do it in the opposite way for yourselves. Okay, that's a good exercise. So let's give a 15 minutes break, then we'll continue.